In the 2013 Flight B summer exam, you've been given a 4x4 matrix which represents the lateral dynamics of an aircraft. Now, it's quite difficult just to take that 4x4 matrix and take a closer look at each of the flight modes, unless you put it into some sort of programming language and calculate the eigenvalues. Now, another way you can work out the eigenvalues is to apply certain assumptions. So in questions A, B, and C, you're given a set of assumptions, you apply them, and then you can work out the eigenvalues for the roll mode, spiral mode, and for the Dutch roll. So for part A, for the roll mode, the assumption is that we're just looking at a system where we're just looking at the roll mode only. So we're only looking at the rolling motion. There's no side slip involved. So what that ends up meaning is that, so normally the side slip is represented as your reference side slip, and any sort of disturbance, a linearized disturbance. So setting the whole thing to 0, the disturbance can be taken as being 0. So in that case, if you got the rate of change of your side slip disturbance, which is equal to your rate, that will equal 0 as well. So you can take those two simplifications, apply it to the roll rate equation that you've been given, and you end up with first order system which simply looks like that. Now, to form first order, so this represents a first order time domain system because it's actually, so if you were to take a first order system and get the first order time response of it, the time response is normally in this type of form. So you'd have disturbance amount of something until, so it'll start off until it gets to some sort of steady state. Now, the way first order systems can be characterized is you've got a time constant, tau, which is the time it takes for the system to reach 63.2% of the total amplitude. So in order to work this out, you need to work out tau of this system. So for this system, LP is 5.22, so you can get that off the 4x4 matrix that you have. So this would equal so in order to work out the time constant, you can usually convert this into a Laplace domain. So this would become the roll acceleration becomes SPS, right, 22, which is equivalent to so what that says is that you've got a first order system with a real pole at negative 5.22. So if you were to draw that out, and your time constant, so that value, the negative 5.22, is equal to negative 1 on tau. So tau is actually just the inverse value of that, which is about 0.19. So this system would take approximately about 0.9 seconds to reach its steady state value. So that gives you the first one for the roll mode, so you can tell that from this the roll mode is stable. In terms of the second one, the spiral mode, you've been given a slightly a different set of equations. Here the assumption is that during a spiral the roll rate remains constant. So again, if we apply that, delta so your roll rate P is equal to some reference roll rate, which is your constant roll rate, plus delta P. So if your roll rate remains constant, P would just equal P0, your reference value. So you know that P is equal to 0, which means that if delta P is equal to 0, the rate of change of that, which is delta P dot, is also equal to 0. So you can apply both of those back into your first equation. So you end up with, well, into equation 2, and you end up with the following simplification. So what you can do is, once you have that, now with a spiral mode, you're only looking at your yaw rate. So if you're going to look at your yaw rate, the idea is to rearrange this, get it in terms of your side slip angle, substitute that value back into your first equation in order to get another time domain differential equation in terms of your yaw acceleration. So by rearranging this equation, your side slip angle can be represented as negative LR delta R on L beta. So you have this value, you can take this and you can substitute it back to equation 1. So your equation 1 now becomes again, your delta P remains 0, you have NR and your linearized disturbance in terms of yaw rate. So you can go through, you can do a couple of steps to simplify that down. And what I've done is I've put them both, so the NR L beta is now divided by L beta as well, so you have a common denominator. So then what you can do is you can take the terms that you have, move this onto the left hand side, so again what you're left with is a first order system. So this value, if you go through and calculate it out, comes out to be .857, and once, so again you can rearrange it in a similar way to what we just did with the roll mode for your spiral mode. So if you apply a Laplace transform to it and rearrange, you'll end up with the following equation, and what that means is you've got another first order pole which is going to be stable because it's in the left hand side of the plane. It won't have any sort of oscillatory effect, so it'll be subsidence only, and you know that tau is going to equal negative 0.857, so 1 over 0.857 which is equal to 1.167 seconds. So if you draw that out in terms of time domain, tau will equal that. And as you can see, the spiral mode is much faster motion. The spiral mode is more of a slow type effect in comparison to that. So the last one, so part C, is your Dutch roll mode. So the easiest way to do this one is to make sure that you do the calculations at the beginning. All you can do is you can pull the value straight off the 4x4 matrix, place it into this. So once you have it into this form, in order to work out the eigenvalues, you can apply the determinant equation. So again, from page 195 of Nelson Flight Stability and Control. So you've got a 2x2 identity matrix multiplied by lambda, giving you the following matrix, and then you're going to minus it from your A matrix. So that would be x star, that would be your state matrix. So you're left with the following matrix. So taking this, you can now perform the determinant. So that's AD minus BC will give you lambda plus 0.158, lambda minus 0.47, and it's going to be plus 1.846. So if you expand that out, you're left with the following. Now the eigenvalues of this characteristic equation are negative 0.314 plus minus 0.3497 in terms of the complex component. Now if I was to plot that in an S-plane, I would end up with this so this actually tells me that it's in the left hand side of the plane, it's going to be stable, and using that information I know that it'll be underdamped. So now I know I can calculate out the damping ratio and the natural frequency by applying the ideal second order equation, which is just lambda squared plus 2 zeta omega n lambda plus omega n squared. Now I can compare each of the terms directly, so I know that 2 zeta omega n is going to equal 0.628, and omega n squared is going to give me 1.923, which results in an omega n value of 1.35, and then you can substitute this back in here to work out your damping ratio, which is 0.232. Now the other thing you're asked to do was to calculate out the settling time. So the 95% settling time rule is 3 on zeta omega n, which is 3 on negative 0.314, which is equal to 9.55 seconds. So this information you can use to work out that, okay, it's highly underdamped and will die out in about 10 seconds. So once you have all this information, the final step is to represent it all together on one pole zero plot. So I know that the roll eigenvalue is negative 5.22, spiral was negative 0.857, and for the dash roll, the eigenvalues were negative 314, so it was a complex conjugate fair, and J 1.3497. So because all three are on the left hand side of the plane, you know that you've got all the lateral modes for this aircraft are stable, and then you've got a set of information that we went through earlier in terms of the roll has the fastest subsidence, followed by the spiral, which is much slower, and the dash roll, which ends up, the effects die out in about 10 seconds.